Thank you for all coming to this special origin seminar. Today we have our speaker, Wang, a fourth-year grad student from Tsinghua University at Beijing, worked with Chris Allen. He's visiting us from New York because he's currently at the pre-doc fellow at CTA. Today we will hear him from as the talk, a journey of ice, a view from planet formation. And the floor is yours.
Thank you for having me there. So as already introduced, I'm a PhD student from Tsinghua, and I'm primarily working on hydrodynamic simulation with compositional delivery in disk to planet in my PhD. But in CCA, I also work with field worry on resolving circumplanetary disk in global simulation. So if the time permits, in the end, I will show you some movie of figures of cool CPD. But let's start. Okay. So planets are born in protoplanetary disks, and in a cooperation scenario, we know small grains, they have to go through a series of goals to finally form a planet. So for example, you should have millimeter-sized pebbles, kilometer-sized planetesimals, and of all this material, the small pebbles are of great importance because it participated in various growth process. Like pebbles can be accreted by the planet directly, enabling fast pebble accretion growth. And pebble can also gather together to trigger instability in the disk, directly form bigger bodies. In fact, the way we first saw the image of our protoplanetary disk coming from ARMA, also review the thermal emission of pebbles. And over the last 10, 15 years, there are many ARMA large programs targeting at the disk, providing us a diverse picture of the disk, especially in the density distribution of pebbles. And we see there are many disks. They are compact. Also, there are some very big and has more substructures. But from hundreds of AU to the inner 10 AU, we see pebbles are everywhere in the disk. And all these nice pictures and great importance of pebble comes from their rich dynamic in the disk. So in the disk, pebble feel the gravity of the star, especially at the vertical direction. So they tend to settle to the midplane. On the other hand, when they are doing capillary motion in the disk, pebble feel gas drag, losing their angular momentum and gradually drift towards the star. Additionally, I want to stress that pebble contain multiple compositions, both the volatile ice and the refractory. So the volatile will sublimate whenever the disk temperature reaches high enough, they become vapor. And if you put this process back into the disk, the specific location where pebble sublimation happens is usually referred as disk snowlines. So like shown on the right, you see the sharp transition of the gas abundance of different molecules like water, carbon dioxide. So that denotes that sharp transition denotes the position of snowlines. So pebble sublimation or phase change can have important roles in planet formation. Firstly, it will change the composition of solid gas across the snowline. So inside the snowline, like shown on the right, for example, the water snowline, since all the ice is released into the disk, then planet cannot no longer prepare volatile from accreting pebbles. And then they become dry. For example, our Earth is very dry in water when considering the mass fraction. And people think it might imply that Earth should have been formed inside the water snowline. Oh yeah, I forgot to mention, but if you have any question, please just interrupt me. Additionally, there is not only snowline in the disk, but also snowline in planet envelope. Because young accreting planets, they are hot. So when pebbles as a building block of planets will enter the hot envelope, the volatile ice will sublimate and become vapor in the envelope. This process could be very critical because planets, especially small planets, we know they are embedded in the disk. So their envelope is not isolated from the disk, but continuously exchanging material with the disk. And this process is called hydrodynamic recycling. The recycling is enabled by the complex hydrodynamic flow in the vicinity of the planet, like shown on the right. So we have a disk, a planet, and if you zoom in near the planet and shift yourself to a co-moving frame, you will see this sharing flow aside and the hot shell orbit where material comes in and comes out. And that accounts for why we have the recycling here. So then the fate of the vapor being preserved into the envelope finally become part of the planet, or being carried out by the recycling flow lost to the disk will eventually determine the composition of the planet. Secondly, this change could assist planet formation as snowline. In the disk, we know small dust grains like micron size, they can grow by collide with each other and stick each other. But when the solid body grow up to centimeter or millimeter size, then collision will no longer lead to coagulation, but more at fragmentation. So they break up. And this is the point where people think, okay, we should have some instability kicking to directly form planetesimals from these small bodies. And so one of the famous mechanisms is streaming instability. See, Andrew did the pioneering works here. And here is just snapshots of typical streaming instability simulation. You see, initially, you have some small perturbation of dust and gas in the disk. And with time, they grow to this coherent stream. And finally, at the bottom of the stream, you would have very high solid density, and eventually you can climb to form planetesimals. So there are tons of studies to try to examine the perfect location of suitable environment to trigger this instability. And people generally found that you need a large solid to gas ratio, which is perhaps around unity. So, but this is extremely large because considering the solid to gas ratio just in the ISM is nearly 1%. So where can we get such a large solid enhancement in disk? Well, snowline can do it. Snowline can induce solid pileup, and this can be done in many ways. But one of the ways is a so-called vapor retro diffusion scenario, work as follows. So imagine you have pebbles across the snowline, the ice sublimates vapor deposit into the disk. The vapor can diffuse. It diffuses in all directions. But when it diffuses afterwards across the snowline, vapor will recondense on the pebbles. So in this way, the volatile are effectively trapped near the snowline, accumulating solid material, and finally, you would have a bump of solid to gas ratio just outside the snowline, like shown on the right. So snowline is at around 2 AU. So in previous 1D studies, people found this mechanism can readily elevate the solid-to-gas ratio to unity, which is enough for streaming stability to operate. And lastly, but not least, phase change can alter temperature structure. And this is done by latent heat absorption. So latent heat absorption refers to the process that when you sublimate the ice, you need to absorb energy. And this is very common in our daily life. Like when you want to keep boiling a water, you need to keep heating it. You need energy. So let's consider just a real disk. In a real disk, the temperature structure should be determined by various heating sources. You have the stellar irradiation. You might have viscous dissipation at mid-plane, but also at snowline, you will have latent heat. So all the temperature sources will determine the temperature structure, thus the morphology of the snowline. So given the different morphology, you might also expect it will also influence the pile-up stress we get from previous mechanism. So till now, I mentioned lots of important roles of phase change in the planet formation, and all of them actually are related to important planet formation questions. For example, we know snowline change the composition across phase change the composition across the snowline. But do planets from the outside the snowline doomed to be wet? Also, we have solid pile-up snowline, but how feasible is it? How robust is it? We always have planetesimal formation preferentially there. And lastly, if we alter the temperature structure by phase change, can we really observe it? So,
sorry, can I ask, is it, I don't know if you have these numbers on the top of your head, but for latent heat to like compete with stellar irradiation, you have a sense of like at some location, I don't know, an AU, whatever, however many AU, like how many Earth masses per year would need to condense to have the same energy as?
Yes, that's a very good question. So, I would say criterion for it, so you need to be more or less optimistic where stellar radiation contributes little, and you need to have relatively large dust-gas ratio so that your latent heat energy can actually be some fraction of the gas energy, and that dust-gas ratio might be like 10% each. Yeah, so which is relatively high, but not unpredictable.
Yeah. Okay,
Thank you. Yes, later I also show this. Okay. Yeah, so to address these important questions, we not only need a phase change, because we also need the hydrodynamic flows because it interacts with each other. Like we have planet disk recycling flows I mentioned to you before. In the disk, we also have these accretion flows. So that's why we need to actually do phase change in hydrodynamic simulations. So how to do it? I just briefly go over this, but we have multi-components. I mentioned in this process we have gas, we have solid, and solid contain volatile and refractory. So to capture this, we apply a multi-fluid dust module implemented by Pinghui and Xuning in Athena++. So each composition corresponds to a dust fluid. For example, the pebble has at least two compositions, and they are represented by two dust fluid. And given temperature, this configuration of solid gas, it should be in equilibrium. But if some phase change happens, let's assume just some ice sublimate to vapor, Then they are shown not only the mass transfer from ice to vapor, but also energy exchange because of latent heat effect I mentioned. So naively speaking, if you sublimate something, your temperature should drop. And you also, because you inject vapor into the environment, you should have molecular weight increase. And this new configuration will lead to a new direction of phase change. So in practice, we need to iteratively solve for this process until some equilibrium is reached. And okay, with this module developed, we can answer some questions. So first, are planets from outside snowline doomed to be wet? To examine this question, we can put a planet, a small super Earth planet outside the snowline. So we put it at 4U, while in our disk model, the snowline is at 4U. So, this is the movie of our simulation, and so the red line, sorry, the planet is at the center, and this is in a co-moving frame of the planet. We see the red band, this denotes where pebble comes in, and you will see the blue color denotes the density or fraction of ice, and the red is for vapor. So let me play the movie for you. So we put the planet here, and later it grows. So we have material coming on, and because when planet grows, it becomes hot in the envelope. Then all the incoming pebbles, they graduate to sublimate to vapor, as shown in the red in the middle. And in the meanwhile, vapor can also be carried out. Let me do it again. It can be carried out by these flows. And whenever it is the vapor enter the outer cooler region of the disk, it will recondense as ice grains, shown as the blue band. So let's repeat the process. Is that we have pebble comes in, sublimate, vapor carried out by recycling flow, and recondense as ice grain. So in this simulation, you can see the reach a steady state very quickly, which means all the incoming pebbles is fully compensated by the outgoing ice grains. So there's no net accretion of ice anymore, even if the planet is outside snowline. So eventually we can just measure the vapor fraction in the envelope, and it is very small, so we get a really dry planet.
Yeah. This is a good question about what's going on in the inner boundary here.
This one?
Yeah, is there influence, or is it just a static, a softened potential, or?
It's we don't have a softening of potential, but we have a refractory boundary. Yeah.
So it has to reach steady state then, at some level, right? You can't accrete.
But you can. So the steady state means here you have a steady state in vapor fraction. Right, the simulation can reach steady state, but later on I will show you a simulation that never reaches steady state.
In vapor fraction.
Yeah, and also in its dynamics, you can see. Yeah.
But you're saying that, but I guess, I mean, this is a problem we've seen in a range of masses, that basically at some point you stop accreting.
Yeah.
Because of that choice of a reflecting inner boundary.
Yes, of course, yes. But suppose if you always have vapor injection into the envelope, then you cannot be steady. And here you become steady because your vapor fraction reaches a certain amount as it stops here. So that's a steady state in terms of vapor fraction. Yes.
I was going to ask the size of the pebbles, if they're very big and.
We have like just fixed Stokes number, like perhaps 0.01, like millimeters size.
But if they were very big, they could deliver the ice reasonably.
Yes, that's right. They can go deeper in the envelope. That's right. Yes, because they feel less gas drag. So here, many pebbles they eventually rotate near the planet because their stopping time is 0.01. But if you have a very large stopping time, it might hit the planet itself directly. Yeah.
So I guess that's in addition to the simulation issues, I wonder about some geophysical issues. You know, these atmospheres are very hot at their base, since you probably have this magma ocean.
Yes.
I don't know, people, this is not my expertise at all, but I know people have worked on how volatiles can then get incorporated in that magma ocean.
Yes.
So could vapor build up that way?
Yeah, I think so. Yeah, you could, I mean, you can, like you saw, you can have some vapor in, then it absorbed by magma, so more vapor in. I think that's possible. That's total. Yes.
I know that's a very different study, but I just wanted to, yeah.
I think that's a good idea. Yeah.
I guess, how does the recycling work in 2D? Because if I remember correctly, like Mel 2013 does like 2D recycling. And there's like a strictly bound region. So is the transport of volatiles back outside of this bound region strictly determined by like a diffusion at that boundary, or?
Yes, so you can see it here actually. So you, the orange line is where I sublimate. Well, the blue line is some kind of the boundary of the bound atmosphere. So inside which the material should just rotate around the planet. Then here the recycling time is very long, right? So, and in this case, it is that all the material, they are already sublimated and recycled before they reach the boundary. So that's what happened. So I would say, yeah, that's also limitation of 2D case. You're in 3D, you have all these complex flows. Yeah. And might bring more surprising thing. Yeah.
Are those incoming streams already sublimated?
These streams.
Yeah.
They kind of sublimate beginning somewhere, and they finally get all sublimated at the orange line.
Okay.
Yes. Yeah. Okay, let's move on. I think, and things will become completely different when we move the planet. The same setup from 4U to 5U, just 1U further, but then the disk get a little bit cooler, right? About maybe 10 Kelvin. The disk get cooler, then you can imagine the planet also get a little bit cooler. Then your eyes will go deeper into the atmosphere to sublimate. So this is what will happen. You have all the ice spiraling and get sucked in to the very central region of the planetary envelope. And in this process, you can see the vapor fraction actually keep going up, keep accreting ice. And if you look at a little bit more from the beginning, you can see the sublimation radius, so this orange line, it gradually shrinks. And that's because when you sublimate, you need to absorb latent heat. So you cool down the atmosphere effectively. On the other hand, you can see the rotation region of the planet, which might be denoted by the red region. It actually gradually expands. So the atmosphere itself, the bound atmosphere expands. And this is because when you pollute the atmosphere, the mean molecular weight increase, so your pressure support drops. You have to have more rotational support. So you have a divergence evolution of the two radius. Sublimation radius shrink, atmosphere expand. Then you actually get easier and easier to accrete ice instead of recycle it. So that's why we actually observe the positive feedback to obtain more and more water. And the simulation never reaches steady state at the end of like 500 hour wait we have. Yes.
And I said another question about the other thermodynamics in the simulations. How are you doing the heat handling overall?
Yes. Yeah, this is just the adiabatic equation of state. And although we do encounter the effect that your gamma changes with different vapor fraction.
So you do include that? Said?
Yes.
Yeah.
Yes, we do.
But there's no cooling.
There's no cooling. There's no cooling.
So how do the temperatures in your atmosphere do you think compare to what you would find if you were to calculate?
Radiation transfer?
Yeah, like cooling rates.
That's a very good question, but you would imagine in the very inner region, this planet is very possible to be optically thick. Yeah, it's very dusty. So it's possible it's okay calculation, but at the boundary it might be have some more issues, I would say. Yeah. Okay, so yeah, the reason why we have all the water because the atmosphere itself is much larger than where we get all the material sublimated. So that to sum up, we have a relative size of atmosphere and sublimation radius that determines the recycling efficiency of volatile. And we have a sharp transition of planets being wet and dry outside snowline if you just move them nearly from 4U to 5U. So that might implies the possible compositional dichotomy of exoplanet population. And we have some evidence. Interestingly, recent high-resolution radio velocity measurements of small planets around M drops, they show this compositional dichotomy lines. For example, you have many planets lying across the Earth-like composition line. So this is an MR diagram, sorry. And you also have some planets lie closely at 50% water composition line, which people refer them usually as water worlds, but there are a few planets lying in between. So we think that might be a sign, but we also know with more and more data, this problem itself becomes complex. So I'd like to discuss with you later if you want to. Yeah, have more ideas on this. And another important implication, if we go back to the initial question, like we have Earth, can Earth form the dry outside the snowline? So in fact, people think mostly from theoretical side that over the first several million years after so the formation of our star, it actually keep contracting, so the luminosity decrease. And that means the disk will become cooler and cooler, and the snowline inevitably drop below 1 AU, where our Earth is located. So that means my Earth should have accreted some more volatiles. And when it doesn't do that, we think, okay, recycling can do it. Even if the snowline is just inside 1 AU, Earth can still be dry just due to the recycling. So in 2021, Ernst Johansson showed that if you include its recycling process, your Earth can only get its water at the beginning of accretion, and after that, you can only accrete dry pebbles. So your kind of this is ice fraction drops down, and that could match our current day value. Okay, let's shift a bit. We move on to the second question. Do planetesimal form preferential as snowlines? So I show you in the introduction that in previous 1D studies, this is very promising. We readily reach unity, but the question is, the snowline is not 1D. It is at least 2D, right? We should have some vertical structure in the disk. For example, we should have vertical temperature structure. So in a classical disk, we have stellar irradiation, which generally only penetrates the upper layer of the disk. Then the upper layer is hotter than the mid-plane, and we usually call it as like a passive disk. But if you have like certain dissipation of energy around the mid-plane, mid-plane will become hotter, then we usually call it active disk. So given this different disk temperature structure, you would have different shape of snowline, which might influence the strength of the pile, right? So we conduct a 2D snowline hydrodynamic simulation of different kinds of disk and include or excluding also the latent heat effect, since it also influences temperature. And yeah, that's our overview of what would like in our 2D simulation. So still we have all the vapor in red and ice density in blue. and we release pebble from the outer boundary like the foil-ish and let it drift in. So as a pebble drifts in, when it reaches in the hot region, the snowline, it will sublimate to vapor. And so in between the red and blue, we see this green line that actually denotes the actual shape we see for a 2D snowline. So the streamlines you see are actually denotes the flux of pebble and vapor. With time going on, you gradually see just outside the snowline, there's the ice density gradually increase, and that is consistent with previous study. We have pebble up there. So you can compare the case for an active disk and a passive disk. So their snowline morphology looks distinct because in the active disk, your midplane is hotter. So you have further out midplane there, and you also have a protrusion of snowline upper layer where it is cooler. Given this different morphology, we wonder whether it could bring different strands of pebble. So we can quantify this by just measuring the peak dust to gas ratio at the snowline, also the mass of ice stored at the snowline. So that's shown on this diagram. So y-axis is the peak dust to gas ratio, the color is water mass stored. And this is for a typical 1D study previous people shown. It already can elevate the dust to gas ratio compared to a normal disk in snowline. But our 2D simulation generally give you actually overall enhancement of it. If you see, this is our 2D simulation, this is 1D corresponding 1D study with a similar parameter. More interestingly, we see active disk has a larger pile-up strands than the passive disk, both in the dust to gas ratio, also the water mass. And I'm going to explain why is that. So imagine, so you can get a sense of it by just looking at the streamline of flux. You can see in the active disk, there is a strong settling of ice, but this is absent in passive disk. We don't see this. And so the story goes like this. Imagine you have something sublimating at a snowline, you release vapor, then vapor can diffuse to upper layer, although it diffuses in all directions. In a passive disk, when vapor diffuses to upper layer, since the upper layer is hotter, nothing will happen. The vapor is just accreted to the star. But if in an active disk, you diffuse to upper layer where the temperature is a little bit cooler than the midplane, then you will recondense on the pebbles there. So you recondense on the pebble, grow out the pebble a little bit, then that triggers the stronger settling. So all your pebbles go to the midplane again and drift across the snowline and sublimate. So these cycles goes on and on. So we are trapping the water near the snowline. Yeah.
So what's the vertical temperature profile like in the active disk? The passive disk is vertically isothermal?
Yes.
What is the active disk, does it get hot again at the top? I'm just wondering about the
Yes,
of the
yes, it
vapor.
is. So it's like active should be hot here, cooler region, and hotter again. So because so in the optical thick region, it is hotter in the midplane, cooler in the upper layer. But when you go optical thin, of course, going to upper layer is hotter.
So you are including radiation even in the active disk?
Yes.
Okay,
yes,
okay, so it's
yes,
on both, okay.
yes.
But is that why we see that? I guess it seems a little low, the place where the vapor fraction is increasing.
You mean here?
The red lobe in the active disk. I guess that's the part that's sort of.
Yeah, that's because all the vapor will kind of sublimate. Condense there. Yes. Your hot upper region is even higher. It's not included in this figure. Yeah.
Can you remind me then the very upper region is hot because of heat from the star,
Right.
even in the active disk?
Yeah, even in the active.
And that's why it's hotter.
Sorry?
And that's the reason it gets hotter because of the stellar heating.
Yes, and you cannot cool efficiently, and there's no dust there.
It's actually, see below
Yes.
where this tongue of blue, it's
Surrounded by the.
Okay, I have something like this.
Okay.
Great. Yeah, yeah, so this is a cooler region.
Yeah,
Yeah, so you likely your vapor when they go into it, they will condense.
but is that, so the orange part only exists at like 1.5 AU, half hot, but it's blue everywhere.
Okay, maybe sorry, I'm confused. I think it is lower because your temperature profile, imagine you versus you have whether you isothermal versus you have like something hotter in the fan called the upper layer, your skill height shrink a bit.
Yeah.
Yes, that's the reason, sorry.
Can I ask about those meridional circulations? So I mean, that's obviously the latent heat is playing a role. Is there anything else involved? Like is the dust feedback important or?
I think, yeah, your dust need to grow a bit to have the settling. That's also one aspect of it. But in terms of energy that driving this cycle, it could be latent heat. Yes. Yeah.
And you have grain evolution here, you have red or your big size pebbles for mine?
So we did it like we release constant size pebble from the outer boundary. It doesn't coagulate the fragment, not at all. But it can grow a bit just by recondensation and sublimation. Yeah, that's it.
But it's fixed size, not fixed dose.
No, it's fixed size releasing from the outer boundary, but its size changes whenever it is. Yeah.
But an active disk should of course have a net accretion rate of gas flowing through. Is that consistent with this, or would that be an extra effect, or? Like when you have the active disk, is it accreting as well, or is it not?
So we have the same accretion rate in both disks.
Is it okay? So they're both,
Yeah.
even the passive disk is accreting. Okay.
So the only thing we change is like the opacity. So if you have a higher opacity, then the disk heating is harder to get out. Your mid-plane get hotter. That's how we play the trick here. So they are like controlled in both pebble flux, snowline position. And they still show the difference. Yeah. And the previous simulation, there is no latent heat, but here we include it. So it seems still active disk, but we just look at the temperature profile this time. So if I play the movie, we see when pebble drift sublimate, also perturb the temperature profile due to latent heat. And this is more clearly viewed if you just compare their mid-plane snowline mid-plane temperature. So for the case with latent heat, you have a plateau of temperature there. This is because of latent heat cooling. So you sublimate something, you cool down the surrounding material, and it tends to keep the material just at the ice sublimation temperature. And so due to this latent heat effect, we actually have a much wider snowline than people would expect. So it's not a sharp transition. We see the snowline likely expands 1 AU, so it's wide region. And of course, you will have a wide snowline. You can imagine will have the same pebble flux. Your peak dust to gas ratio will drop a bit. That's a consequence. So as long as I see this plateau, I was wondering whether it could have any observational features. So actually, you could do just a very rough radial MC. Radial MC 3D calculation. You see, at the T plateau position, you have this also some feature in intensity. And then we can consider whether we can observe it in real observation. But you can immediately say, it's infeasible because snowline is like just 2 AU. Even for the nearest star formation region, we need like 0.01 arc seconds resolution probate. So it's definitely infeasible in Alba for solar-like star. But what about hotter disks? So the last question is whether we can observe a temperature plateau as a feature of snowline. Our answer is we could, but should be observed only in outburst disks currently. So outburst system refers to a group of young stellar objects that has its luminosity increased suddenly by several magnitude in a very short time scale. So for example, the famous FU Orion system, we see it is rising of luminosity is only within 1 year and have 6 magnitude difference. So you can do some spectroscopic measurement or modeling of this outbursting system. And people find all the spectral feature can be explained by a rapidly accreting inner disk. It releases so much energy due to the high accretion rate, so that it actually outshines the star itself. So instead of having an outburst on the stellar photosphere, you actually have the outburst in the disk, in the inner disk. Then a direct consequence of that is you move the snowline from 2 AU to tens of AU. Then we think, oh, ARMA can resolve it possibly now. And there is a special source, it is 3 Ori, which is among one of the most well-observed system. People, the current luminosity of it is like 200 times of solar value, which is very hot. And people found at 40 AU, it's not very clear here, but you see there is an intensity dip in the disk. If you look at its profile, really profile of the intensity, so among this band, you see the intensity dip is actually looks like more like intensity plateau. So there are many ideas on what causes this intensity dip. So the simple ideas would be if you are observing the intensity, which denotes the density of dust. So the intensity dip means you have a sharp transition of pebble surface density. So how to get this transition of pebble surface density? You can have a sharp transition of pebble size or pebble property. But recent observation, especially multi-band observation of the disk, show us that so you can measure. So this is a plot of the spectral index of different wavelengths combination, and a sharp, usually a sharp transition of pebble size would reveal itself in a sharp transition of spectral index. But we see what you see here is nothing. It's only like just a little bit increase around just 40. There's nothing special of it. Also, if you look at the molecular emission of rare species, you see there is an intensity depression at the inner 40 AU, which implies it is optimistic in the 40 AU. So your intensity should not represent surface density, but temperature. So the intensity dip we observe should be a temperature plateau. And so we try to examine this feature, just give you some proof of concept simulation idea. For this system, we don't directly observe it outburst the rising phase. But what we only know is that it is dimming down. So current day is like 200 of solar value, but 20 years ago it is brighter. So we can run this simulation. So again, this is a luminosity profile up to today. This is a mid-plane temperature profile we see. So if I start the outburst, the luminosity would rise very quickly within 1 year. Then you see all the ice is sublimated up to like 60, 70 AU. Then the luminosity decrease in the dimming phase, and your snowline gradually retreat. When it retreat, the ice, the vapor will recondense to ice, and you release latent heat during the process. And that's why you gradually see this plateau developing, because due to latent heat, you want to make everything the same temperature, similar to the vapor ice sublimation. So you can definitely see, at the present day, luminosity value, we are not reproducing the plateau, which is at like outside 40 AU, but so we need more parameter tuning, but at least we show we can have a snowline, which is have a snowline region of 20 of AU long. Okay, that's pretty much actually all of my main talk. So I have introduced you, we have phase change module developed in Athena++, and applying this module to the disk, to the planet accretion, we found a volatile water accretion by recycling, and applying it to the disk, we identify a water cycle near the snowline, help building solid pebble up, and we found latent heat, we created a temperature plateau. And these are all related to the crashing like implications. Give you here that we think recycling is necessary for Earth to form dry outside snowline. And snowline served as the Z site for forming planetesimal because we have a huge leap from 1D to 2D simulations. And eventually, if you believe me, I think the intensive leap in V83 is a temperature plateau. Do I still have some time? Like 5 minutes?
Yeah, sure. Because people have already asked some questions.
Oh, okay.
Can I ask you a quick question before you move on?
Yes.
So you said something at the beginning about the high accretion rate in the inner disk contributing to the bumpy luminosity and outshine the photosphere.
Yeah.
But of course, whatever material is accreting through the inner disk falls onto the star and then should generate accretion luminosity.
Yeah.
Which should be of the same order of magnitude.
Oh, yes. Yes.
So are you including heating, are you including a spike in the stellar luminosity as well, or you're just putting all the heat in the active disk region?
Oh, sorry, I may confuse you. So what we did is just we just include, increase the luminosity, stellar increase the irradiated luminosity. So
Okay, so you're not, yeah, so it's not, it doesn't matter, the details.
Yeah, it doesn't matter.
It's just the star is bright.
yes,
Okay.
yeah, because it's very in the region, 0.1 AU-ish.
Right, okay.
Okay, yeah. Just like, because I promise you, if I have some time, I want to show some work from CCA who sponsor my trip this time. So yeah, so our work show so understanding the material delivery in the disk and from disk to planet are the key question in planet formation, right? And our previous work just highlights the importance that you need to include the phase change in hydro simulation. So we talk about this, we talk about small planets, but I haven't talked about anything about giant planets. So the difference for giant planets is that when material gets accreted by the planet, it will fall on possibly on its disk first, and then get accreted to the giant planet. So just as an analogy to circumstellar disk, we have a circumplanetary disk. So to understand the accretion rate to the giant planet, we need to understand the material delivery from PPD to circumplanetary disk and in the circumplanetary disk. And that raises a challenge in simulations because we need to resolve both the global disk, but as well as the CPD down to the planetary surface, which might give you a scale separation of 10,000. And the current simulation doesn't reach that high. So the best practice we have, we can only resolve 0.1 U radius of the Jupiter, but for example, the Jupiter size itself is like just two magnitudes smaller. So we try to do this in a global disk with rich computational resources of CC, but so we do like more than 10 levels of mesh refinement near the planet. Eventually, we actually resolve down to the surface of Jupiter, which is a white circle here. And this plot gives you like 1 times 10 times 100 times scale set zoom in. But still, we cannot do the simulation directly. It will cost a lot, take a long time. So we did some trick to accelerate a lot. And I'm happy to talk about this with you later. But what we see is that this is a CPD, and it accreting, sucking all the material in its disk. And with time going, the CPD itself become stable in mass. So we have a fixed amount of mass in the CPD, but we see it is very dynamic. You never see a kind of very good steady state. You see all the spirals, they start from the disk penetrating itself all the way towards the Jupiter surface, and there is also some eccentricity excited that never diminish. So yeah, that's all I want to show. And if you are interested in this more, let's talk about this. Yeah. So thank you for your listening. I will leave it here and welcome for any questions.
Have any question for you?
I guess what are the thermodynamics in the last simulations, the CPD ones, are they isothermal or?
It is isothermal, but we like fix the temperature profile in the CPD. So it's not isothermal from the disk to the planet, but we do have an increase of temperature near CPD, but still it's corrected. Yeah.
Locally isothermal.
Yeah, local isothermal. Sorry. Yes.
Can you remind me again how exactly the pressure maximum is achieved in this retrodiffusion model, and how strong the pressure maximum is?
Pressure maximum.
Yeah, for trapping. You trap pebbles at the snowline. Strong exactly how the
It's not by pressure. Presumably, it's by we just have vapor. When they release, they diffuse back onto the outside snowline and recaptured by the pebble there.
Yeah.
So it takes longer time to escape the snowline, right? Then if you take longer time to escape the snowline, you have a pile up building up. That's what happened.
That step I kind of missed. Not quite to get it. Why are the pebbles trapped there?
It's not. I won't use the word trapped because trapped means something you really have pressure on all your pebbles go towards the snowline, right? It's not. It's just when you move a little bit slower. So you just consider you have a constant pebble flux going on. If you move faster, it means your surface density drop. If you move slower, your surface density increase. So that's what happened in snowline.
That's just because the pebbles got smaller. Because they lost their ice.
It's more effectively the vapor is loop around that snowline. So
Just there's a gas pushing back on, the vapor's diffusing back. You think that's the impact of slowing down the pebbles?
It's
The headwind has changed.
sorry.
The headwind has changed.
It actually changed. Yes, I can actually show you this. So let me see if I have a plot for
It's not really pressure maximum. I guess
there is no, but so what we found because I mentioned to you that our 2D simulation has much larger pile up than 1D, but the main reason is actually if you encounter hydrodynamic effect, you have an outflow of gas at the snowline, This is like just you can imagine you dump vapor at some position, it will viscous spreading, right? It spread both directions. It also have an outflow there.
Yeah, I think I got it, yeah.
Yes, thank you.
But you're not actually, you're changing the size, like the Stokes number of the pebbles changing too, like imagine you have some pebbles that
Yeah,
are
it's changed.
existing pebbles and then they grow.
Yes,
Yeah.
they change, yeah.
Right, so like naively, I would think, oh, well, when they grow just to the exterior of the ice line, they would drift faster, they grow.
Yes, yeah. Yes, that's all, that's one of the effect. Yeah, you would have a traffic jam. But in fact, this case actually, the pebble size doesn't change very much. So I think people more like it's like we try vapor and snowline.
Okay.
So the magnitude of the speeds in this flow, are these all comparable to drift speeds or the subcaplarian speeds?
So this black line is the pebble drift.
Yeah.
You can see there's something like this. Yeah. So we can have a traffic jam here, but by this hydrodynamic flow.
Confused by that's in units of sound speed or in units of Keplerian speed?
Oh, this is sound speed, sorry.
Units of sound, but 10 to the minus 3 times the sound speed. That's, I guess these are very small grains then.
Yeah, it's,
Yeah.
yes, yeah.
Yeah. And then these flows are a similar speed. 10 to the minus, these arrows that you have of the circulating flows, are those similar speed to
Yes.
the speed of the grains?
Yes.
Those are like
Yes,
to the minus 3 times the sound speed.
Yes. yeah, so yeah, I mean, the outflow
Half that, yeah.
disorder, that's right.
Yeah.
Yeah, you can make, if you have a bigger pebble, this might not matter so much. Yeah, are we running on time?
Okay, so we're at the top of the hour and you will be staying here today and tomorrow. And we already sent out a sign up sheet. If you want to meet up with him, please sign up. And also we're going to have a lunch with him together tomorrow. So if you also would like to join, please also sign up there. And thank you for attending the earnings seminar. See you next Monday.
Yes.
And if anybody wants to hear another talk on planet formation, there's the TAP, we're gonna switch Zooms because it was sent out with a different Zoom link. For anyone online who wants to stay tuned.
Hopefully that works. I just got a notification Zoom is down like all
Right, bye.
for most people.